In this video, we are going to see about the stability analysis using Routh Hurwitz criterion. A system is said to be stable if its output is under control. Otherwise, it is said to be unstable. A stable system produces a bounded output for a given bounded input. Types of stability: absolutely stable system, conditionally stable system, and marginally stable system. Absolutely stable system: if the system is stable for all the range of system's components values, then it is known as the absolutely stable system. The open loop control system is absolutely stable if all the poles of the open loop transfer function present in left half of a spline. Similarly, the closed loop control system is absolutely stable if all poles of the closed loop transfer function present in the left half of the S-plane. If the system is stable by producing an output signal with constant amplitude and constant frequency of oscillations for bounded input, then it is known as marginally stable system. The open loop control system is marginally stable if any two poles of the open loop transfer function is present on the imaginary axis. Similarly, the closed loop control system is marginally stable if any two poles of the closed loop transfer function is present on the imaginary axis. The system is stable for a certain range of system component values, then it is known as conditionally stable system. The graph shows the marginally stable system, unstable and asymptotically stable. Routh Hurwitz stability criterion: it is having one necessary condition and one sufficient condition for stability. If any control system does not satisfy the necessary condition, then we can say that the control system is unstable. But if the control system satisfies the necessary condition, then it may or may not be stable. So the sufficient condition is helpful for knowing whether the control system is stable or not. The necessary condition is that the coefficients of the characteristics polynomial should be positive. This implies that all the roots of the characteristic equation should be negative real parts. Note that there should not be any term missing in the nth order characteristic equation. This means that the nth order characterization equation should not have any coefficient that is having zero value. The sufficient condition is that all the elements of the first column of the Routh array should have the same sign. This means that all the elements of the first column of the Routh array should be either positive or negative. If all the roots of the characteristic equation exit to the left half of the S-plane, then the control system is stable. If at least one root of the characteristic equation exists to the right half of the S-plane, then the control system is unstable. This table shows the Routh table and how to calculate the table using the coefficients given in the problem. The special cases of Routh array is the first element of any row of the Routh array is 0. If any row of the Routh array contains only the first element as 0 and at least one of the remaining elements have non-zero values, then replace the first element with a small positive integer epsilon, and then continue the process of completing the Routh table. Now find the number of sign changes in the first column of the Routh table by substituting and tends to 0. All the elements of any row of the Routh array are 0. Write the auxiliary equation of the row which is just above the row of zeros. Differentiating the auxiliary equation with respect to S. Fill the rows of zeros with these coefficients. The problem shows how to find stability using Routh Hurwitz criterion. The example shows how to find the Routh Hurwitz criteria for stability. Thank you.